Hey everybody, today we are going to solve another daily LeetCode challenge. So today we got a hard one and the problem is number 1192, critical connections in a network. So the problem is we are given a not-directed graph like the one that you can see on the left. In order to explain the problem, let me define a graph myself. So here we are given a not directed graph. And the task is to find all edges that if we remove them, it will convert the graph into two separate connected components. So what does that mean? So in the problem, it is called, those edges are called critical edges. So for example, here on the graph that I just draw, if we remove this edge, it will convert the whole graph. So initially, the graphs in the problem are a single connected component. But by removing this edge, it will convert the graph into two separate connected components. So all edges on, so we can component 1 and component 2, all edges in component 1 are reachable from each other, but none of the nodes in component 1 are reachable to component 2 and vice versa. And as you can see on the example in the problem as well, so if we remove this critical edge here, it will convert the whole graph into two connected components. One of them has 3 nodes and the other one has only 1 node. So in order to solve this problem, I want to use Trajan algorithm. If you don't know what that is, so I will put a link in the description as well, but the whole idea is very similar to a DFS. So we are going to traverse this graph using DFS, but with a few adjustments. So let's first let me explain the algorithm briefly. So here's the algorithm. So initially, let's say we are assigning a ranking to all nodes. So initially, I just assign infinity for the ranking of all nodes. And we start the DFS traversing the edge, this graph from node 0. And then every time we are visiting the node, we are updating. So initially, we update the node 0 with the ranking 0. And then we start the traverse. So here, after that, we visit 1, and every time you're visiting a neighbor node, we just update the neighbors. You're informing the neighbor that the ranking was 0 and your ranking could be 1. So since this node has not been visited yet, because we know by seeing the infinity value in the ranking of the neighbor node, it can be inferred that that specific node has not been visited yet. So we update that with 1, and then 1 has 2 neighbors. So then this is the key here. We can never visit a parent node. We should also, while we are calling the DFS, we should always know what is the node that calling the DFS, or from what node the DFS is being called from. And then you're visiting 2 and then increasing the ranking, so the infinity will be updated by 2. And then, so 1 would be the parent node, and then from 2, node 2 realize that there is a node with a lower value 0, so it updates its ranking from 2 to 0. And at the same time, it informs when we are on the recursion, when we are on node 1, the node 2, it can be inferred on node 1 that node 2 is reachable to a lower value. So if I want to draw it like this, so we visited node 0 and then node 1, and then we went to node 2. But node 2 realized that it has a direct connection to node 0, so it informs node 1 that it has a lower ranking, so it could be reached to a node at lower ranking. And at the same time, that means this specific node, this connection, is not critical because node 2 already found another way to a lower value, to a lower ranking. So that means if we even remove this edge, there must be exist another path from from node 2 to node 1. So this edge between these parent and children, the child 1 and 2, is not critical. If you're confused, so let me implement that, and during the implementation we can see the details of Trajan algorithm here. So first of all, we need to store the graph information. What we are given is just a list of edges in the graph, but as you remember, as we discussed in previous videos, there are several ways to store information of a graph. One of them that we are not going to use in this problem is a n by n matrix that initially all values are 0, and for each u and v in the edges, you just put 1. If the graph is not directed, like this problem that we have here, you just put 1 in uv and vu. So by looking at this graph, we can in this matrix, we can realize that for all 0 values there is no edge, but for all cells with a value of 1, there must exist an edge. But what we are going to use here, so for each node we just assign we keep track of the neighbors for each node in a list. So for example, in this graph we have 1, 2, 3, and then node 0 has 2 neighbors, node 1 has 0, 2, and 3, node 2 has 0 and 1, and node 3 has 1. And this is why it is important to keep track of the parent node, because as you can see, node 2 has 0 on its list and node 0 has 2 on its list. So if we are calling the DFS, we should always know the parent node, so that when it is, for example, if we are going this way, we should know that it is calling from 0, and node 2 on its neighbor list should drop 0 and only call the DFS on 1. So let's first convert that. So for U and V in connections, we want to now have a shared structure to store the graph. So for that, I want to put self and then self.graph equal. So we want to have a structure like for each node, we have a list. So for that, I want to use a default dictionary. Of type list. So that means initially, if the key doesn't exist, it will assign it into an empty list. So and we can simply say for U and V in connections, self.graph of U append V, and vice versa. And also we should keep track of the ranking for each node. So let's say self.rank equal none initially, and then we are updating the rank here, at least infinite value for every node in range of n, since n is the number of nodes in the graph. And for infinity, as the problem says, the number of nodes is between 2 and 10 to the power of 5. So I've designed my own infinite here, inf equal 10 to the power of 6, and then use self.infinite like that. And then this is the step that we want to use, call the DFS function. So the way we are going to call is, we are starting from node 0, so we are going to implement the DFS here, like DFS self. So let me pass that for now. DFS on node 0 with the ranking 0. And what is the parent node? So we don't have a parent, so it is none. So instead, I want to put it here, like the node that we are visiting, the ranking, and the parent, which initially the parent is none. So first of all, we check if the node is already assigned a value and it is not infinite. So let's say if self.rank of this specific node is not equal to self.inf, so that means this node has already been visited and we can directly access to the lowest value of that node. So we can return it right now, self.rank of the node. Otherwise, update, so that means this node has not been visited yet, and we are now updating the ranking of this node now. Self.rank for this node equal to rank. And for all adjacent in self.graph for the node, so these are the neighbors. If the adjacent is the parent, so we want to skip that. So if adjacent equal to parent, continue. Otherwise, we first check if the node has been visited or not. So if self.rank of the adjacent node is equal to self.inf, so that means at the same time means that neighbor has not been visited yet. So we call the self DFS of the neighbor, which is adjacent node, and we are increasing the rank by 1. So the rank is the rank value that we are assigning, and self.rank is a list that we keep track of the lowest ranking reachable from that specific node. And what is the parent for the node? This is the node itself. Here is the parent node for the adjacent node. So I would put node here. And at the end, we are updating the ranking of the node. We should always keep track of the minimum value. So for that, the minimum of the current ranking and the ranking that the neighbor. So remember on recursion, where we finished visiting node 2 and we jumped back to node 1. Node 1 had access to node 0, so it informs node 1 that I have a direct access to node 0, so node 1 should update its ranking as well. So here, this is what's happening here. So the self.rank of that adjacent node. Okay, so far so good. So this is the DFS, and at the end we are just returning the ranking, so similar to what happened here. But what happens now to find the critical edges? If after visiting the neighbor node, if the ranking of the node is still the one the ranking that we initially called it from, or the ranking of the children is greater than the ranking of the current node, so that means this edge itself is critical, because that node couldn't find another path to a lower value, to a node with a lower value at all. So that means there is no cycle from this node to the other one, and this is the only single path that we can connect this node to the other one, or if it is connected to any other node, this is a critical edge. So here, that means if self.rank adjacent is greater than rank, we initially call the DFS width. So that means we found a critical edge, and then we should keep track of all edges. So for that, let me define a shareable list. Answer is equal. So this is what we are returning at the end. But here we are appending all edges that we are finding into that answer. So del.answer.append the node between these two edges. So between node and the neighbor. Okay, so this is everything. Let's try that out. invalid syntax, self dot answer equal. So what is that? Self dot answer all date of list. Just checking the type if we are having any typos. So self.graph default dictionary of list, this is okay. And self.answer equals an empty list initially, and then okay. Line 40. Oh, line 40, the problem is with here. Okay. Okay, there we go. So it got accepted. Hopefully it passes all test cases. Okay, there we go. So that was everything. So I would put the link for Trajan algorithm for if you wanna find more details and read it yourselves. But it took a long time, but at the same time it was a hard problem for today. So I hope you enjoyed it.